just want to confirm you can hear me and see my slides. Great. So thank you for the kind introduction and for including me in this fascinating workshop. I think we have a wonderful day. And I want to add to tell you a little bit about work that my team is doing. I want to tell just a little background. I'm American, even though my name sounds German, and I live in Germany. I grew up in Los Angeles, and I did all my degrees at Stanford University. So I'm trained as an engineer. My PhD advisor was Günther Niemeyer, who was one of the first engineers at Intuitive Surgical. And I worked briefly at Johns Hopkins with Alison Okamura, who you'll hear from later today in this workshop. So stay tuned, stay all the way till the end for the West Coast speaker. She's now at Stanford. And then I was a professor for 9.5 years at the University of Pennsylvania in the GRASS lab, which is a very interdisciplinary lab where I went. My early work was more teleoperation and haptics, and then being in GRASS really brought me more into autonomous robots and tactile sensing and machine learning. And then in January of 2017, I moved across the Atlantic Ocean to the relatively new, we're now 10 years old, Max Planck Institute for Intelligent Systems, and I'm here in Stuttgart today. We have two sites also in Tübingen, and these are just the current staff at my institute. Across the top are our tenured full professor directors, a few of whom also are very active in robotics and soft robotics and machine learning vision. We have group leaders. There's our Tübingen building. This is the building that I'm in right here in Stuttgart as part of Cyber Valley. And I always like to start also by acknowledging my wonderful team, which includes PhD students, research scientists, and postdocs, recently graduated or left and research scientists who are now faculty, and various visitors, including many people who are here in the audience and some core staff. My team, we do research in many areas. We work on fingertip haptics. Someone's not muted, so maybe you want to mute. This is being recorded.
What exactly you want to use it for?
Creative session.
So we work on fingertip haptics, including and wearables. We also work on other haptic interface technology. Recently, we've been doing a lot on benchmarking, grounded force feedback devices, working on shape change and gait rehabilitation haptic devices, still teleoperation, both for surgery, also now construction, working on learning and skill assessment, lots of physical human-robot interaction, different exercise activities, rehabilitation, hugging robots. That was the PhD thesis of Alexis Black, who just graduated, also does some tactile sensing. And then what I'll focus on most today is more our work in touch sensing, both how can we transduce information from the physical world into a robot for it to feel, and then how to make sense of that to actually take action on. And so clearly, whether we're thinking about a human or a robot, vision, being able to see the world around us is critically important. And also hearing, you're listening to my voice now, and you take a lot of clues from the world around you, what you hear. But I think probably most of us, or all of us, agree that our hands and our sense of touch, our skin, are of critical importance if we want to have it take any action in the world, even if that's just clicking the button on my mouse to advance my slides. And haptics, the field that many of the speakers come from, I would define it as looking at both humans and robots and how they interact with the world, also with each other, through the sense of touch. And I think these dual perspectives of how do we create sensations for humans, or how do we understand human touch, and then how do we create artificial tactile sensing systems and artificial tactile algorithms for robots, I really like this synergy, and I'm so happy that these communities are talking and interacting and building on the insights that the others are having. And I would generally divide our sense of touch, something overarching haptics, into two main pieces: tactile, which are sensations that we feel in our skin, and kinesthetic, which come from deeper receptors. So kinesthetic would be more like the joints and motors of a robot, but it wouldn't tell you anything about whether contact is being made, where contact is. This is in the tactile domain. Is it pressing? Is it slipping or shearing? Is there a vibration? Is there a heat exchange? And a lot of the richness of the world around us comes through the tactile cues, but all of it is fused. And often you may not even be able to attribute. There are lots of illusions where different sensations affect one another. But the sense of touch overall is very rich as all these different modalities. Another distinction I want to draw is between dexterous manipulation, which is largely supported by the glabrous skin, the non-hairy skin on our hands, and whole body manipulation. Maybe imagine picking up a heavy box and lifting it up and opening a door or slamming a door with your arm. Our whole body can also do interactions, maybe not as detailed as mine, but we use tactile sensing across our entire body constantly as we locomote, as we manipulate the world. And I'm interested in both And today I'll highlight one project in each of these domains, first on whole body, and then second on towards more detailed dexterous manipulation. If you're not yet convinced, after you've seen these beautiful talks about how good the human sense and animal sense of touch is, robots definitely need better haptic sensors, and they're coming. There's an amazing wave of innovation, and I take a great inspiration. But just to take you back, when I was an early professor at Penn, we took part in the Willow Garage beta program. We had a PR2, and we did some work on using its rather rudimentary but robust and functional tactile sensors. There were just a small number of pressure cell sensors on each of the fingers, and you had to purposely install these, and they could only be read at like 24 hertz, 24.4 hertz, but luckily there was an accelerometer in the hand, in the wrist, and you could use that to get hand clasps, and if the object in the robot's hand was set down, so you could get transients, you get high temporal resolution from the accelerometer, and something about pressing and squeezing from the finger to pressure sensors, but they weren't rich enough to really even identify what the robot was touching. You could pick up stuff without knowing much about what it was. And so working with Trevor Darrell at Berkeley and others, a bunch of wonderful students, led by Vivian Chu, Ian McMahon, and Lorenzo Riano, we added BioTac sensors. And these are sensors that came out of Jerry Loeb's lab at USC for prosthetics, and they imitate the human sense of touch by having many channels. They're biomimetic. You can sort of get shape. It's actually an impedance system going through fluid inside the rubber skin. There's all these different electrodes. You can get the internal pressure, the AC pressure, which is about the vibration, and something about the temperature. But you can't really physically interpret these 19 electrical impedances in terms of forces. It's absolutely not a force sensor. It's closer to a deformation sensor, but even there, it's not so physical. As a mechanical engineer, I'd really like to know, what is this quantity I'm measuring? We love that it's compact, like a half shape, a half hemisphere, but it's very delicate. We have broken so many of these sensors, and unfortunately they're quite expensive. And so maybe robustness could be improved, but we have used these a lot and gotten great benefit out of them, and I want to see the field push even more in this direction. So a few motivating observations that underlie both of the projects I'll tell you about. Physical contact, whether you're human or robot, can take place all over your body. Ideally, I think robots should be able to feel over all of their surfaces, not just on their tiny little fingertips. Softness helps us control contact, moving from position control into force control in contact very quickly, and managing that elegantly, picking it up, shaking something around, pushing a key in a lock. Softness at the interface between the agent and the world is helpful. We also need robustness. We need sensors that aren't going to break when they're subjected to these physical contacts. I personally find that when we want to get higher and higher spatial resolution, if we have to have an individual taxel, a sensing element for each one, the fabrication complexity, just the overall system complexity, gets really high. So I'm quite interested in ways that are maybe more efficient, or can sample over a broad range, or maybe specialized where we can simultaneously acquire data from a large area. And then also we've really had great benefit from bringing in machine learning beyond just physics to get better sensing performance. So the first of the two projects I'm going to tell you about is called ERTAC. It's an electrical resistance tomography tactile sensing project. This is a big project that I'll highlight a few different aspects on, where we're looking at whole body sensing. This work is led by Hyosang Lee, who has been a research scientist in my team and a postdoc since 2017, and he's about to start his independent scientific career on October 1st at the University of Stuttgart as a Cyber Valley group leader. We've had visiting PhD students from Jim Kim's lab and other members of my team, and more recently Juan Bosan, who's here in the audience, and Georg Marces have gotten involved in the learning. And we've published, these are like the 5 main papers, 2 acre papers, a recent Smart Materials and Structures Journal article, Transactions on Mechatronics article that's accepted but not yet published, and we have a big paper under review that I won't talk about, but I'll just hint at. So you can follow up on these. I'll put the citations at the bottom so you can follow up on them if you want. So the main principle, and this is what Hyosang and Kyung-So developed, is that we make a fabric-based laminate, and we intersperse like just point electrodes, and then we apply a current between 2 electrodes, and the current will flow through, and locally pressure changes the electrical conductivity, the resistance locally, and then by taking different voltage measurements from other pairs of electrodes, we can reconstruct, it's a tomographic method very similar to medical imaging, where the high conductivity areas and the low conductivity areas, but with a very simple fabrication approach. And so just shown more closely, we have these conductive patches that are laying through contact resistance on top of a medium resistance fabric. And so by default, the electricity will pass through the lower layer. And if you push, then the upper layer that's very conductive will press in and locally make a really easy path. And so by changing that contact resistance, we can change the conductivity across a large space. We put neoprene rubber on the top to kind of smooth the contact. You can see here we've tried different arrangements of electrodes and proven that having these electrodes in the middle makes a big difference for getting good resolution in the middle. Otherwise, you don't have good sensing. This is what a real sensor looks like. The circuit is sewn with a sewing machine to get the conductive thread going to all the different places. We use high-speed electronics and FPGA to switch all these different pairs. So over time, we inject current and then scan, inject current, scan. So that happens really, really, really fast. We get this long vector of these voltage readings, and then we reconstruct that. In the beginning, we were always doing this with a model. We basically build a simulation and we perturb it, and then we construct the Jacobian around an operating point. So we subtract the expected voltages for a nothing contact, and then we can linearly extrapolate of like where the conductivity is changing, and then we use physical calibration to go from the conductivity distribution into the pressure. And that's actually really important because conductivity doesn't go linearly with force. We also have done a lot with optimizing the scan patterns and using math to say which ones should we recruit. We don't need all of them, and so we have a somewhat optimal pattern. And then here's some results. On the left, this is with the sensor that has central electrodes, and you can see Hyosang pressing. And on the right, this is showing the benefit of that calibration from conductivity to force, where we have a constant mass moving to different locations. It should have this constant pressure profile. And if we don't calibrate, we basically just show conductivity, you can see it really differs spatially, which would be confusing, and we can correct that. And it's very dynamic, it's very fast. We can run the frame rate really fast and have multiple contacts with quite simple and robust physical hardware. We've done lots of performance evaluations looking at 2-point localization, 2-point discrimination. We try to take some inspiration from human touch and overall force magnitude, but this is a limitation. This is only normal force. Kyung-seo also did a really nice study of the transactions on mechatronics paper, where we had the idea of maybe the sensor is scanning everywhere really fast, but kind of cursorily, and then as soon as contact happens in a region, we dedicate more resources, more scanning patterns in that region to get higher resolution. So distinguishing between contact and no contact. And so the sensor is constantly, and this is a nice video of Kyung-seo demonstrating his system. So again, he's going to place weights on it. And now you can look at, these are showing where it's additionally scanning. So there's like a base pattern that's doing overall awareness, and then as it detects contact in different regions, you can see this is the reconstruction. Also, Kyung-seo can go and touch and push in different areas, and the system is constantly adapting to what it feels. And I think that's also a powerful idea, because then we can maybe we can reduce our energy use or reduce our computational load when we're just sort of ambiently aware, but then when something interesting happens, like when you're feeling the circle pressed, we just want to spend our scan time and get higher resolution where we know contact is really happening. And so, the proof of this, the author version of this article is online, and you can check it out if you want. So these were all done with physics, though, because we know the underlying resistance and pressure are relatively straightforward. There's some improvements we can make knowing those physics can help us design the sensors well, but they're invariably factors that are non-ideal. They might creep in slight inaccuracies in the fabrication, slight material inconsistencies, or contact resistance. It just varies in different locations. There are disturbances, the contact resistance, the wires connecting to the soft sensor. It's really a pain, or nonlinearity. And so the longer we worked on this approach, the more we were drawn towards data-driven methods. And so I'll just tell you, this is a ICRA paper from last year, which was our first effort at using simulation and deep learning, where we wanted to say, okay, could we use a deep neural network to go from voltage measurements to pressure distributions? We set up a stage that could press on a sensor, but end-to-end learning, like let's just take these voltage measurements and have to a pressure distribution. You need such an enormous data set, because think of how many contacts are there, how large is each contact, how high is the force. It's enormous. It's just completely impractical if you want to do a multi-contact. And this sensor unfortunately doesn't generalize, doesn't have a good locality principle. That's kind of a disadvantage of this. You really need to know this nonlinearity tomography approach. And so we started looking into building a simulation of this physics of the sensor, and we can synthesize a large data set for a simulated model for various contact cases, and then combine that with just a small amount of real data. And our multiphysics model just has some mechanical and then conductivity, and then also this deformation. And we've compared with end-to-end learning compared to having a lot of simulation data and having this like physics model in there. In the ICO paper, we split the learning into where is contact happening and how hard is the force. More recently, we've didn't have to do that. But here's an example, again, of a pair of weights being placed at different locations, and then what our network outputs. This is just 6 by 6, but we can get the contact locations pretty well. At the time, force wasn't very good, but it was only trained on single contact, or we hadn't done that much. So we did a whole lot more work on a simulation and a different structure of the deep neural network, and that's under review. So hopefully we'll get reviews in a couple months. So this is the first project I wanted to tell you about, this electrical resistance tomography approach to tactile sensing for whole body skin. These fabric-based sensors are robust and soft, and we can adapt the scan pattern if we want to make them more efficient or better resolution. Deep learning has really served us very well, especially to combine the sparse but rich experimental data with simulated data. And we tend to take the real data and transform it into the simulation, so we can have huge files of simulation and just a little bit of experimental data to anchor it in the physical world. And then there are lots of interesting future work that we could explore. But I'll move on to the second project so I can do it justice. So the second thing I want to show you is this new sensor that we've created called Insight. And it's about the size of a human thumb. And this is work by a smaller team. So Juanbo Sun, who's here in the audience. Hi, Juanbo. He's a PhD student with Georg Marcius, who's absolutely brilliant, group leader in the tubing inside of our institute. And we've really had a lot of fun working together as part of Juanbo's dissertation. He'll be graduating soon. If you need a postdoc, I highly recommend you talk to Juanbo. And I'll just briefly tell you, Juanbo figured out really cool ways to fabricate. So we 3D print this metal skeleton, which you can see here, and then he places it in a mold and overmolds it with just a single layer of opaque but shiny polymer of silicone. It's very thin and very sensitive, and the skeleton is inside, so we don't have to have any layers. It's very fast and robust fabrication. And then a camera, I forgot to highlight, there's a camera with LEDs, multicolor LEDs, looking up inside the finger, inside of Insight. And you can see this is the sample image. And then our network can compare that with the reference image. And we label, we have a test bed, again, a 3D printer with a two-jointed motion stage, so we can take a lot of data with about 4 millimeter diameter indenter, and each one is labeled with a little pressure distribution of where the force, and we measure the force. And we're here doing not just normal force, but also shear. So the indenter comes over and touches Insight and presses into different levels, and also applies traction, translates in different laterally. And then our network learns to predict these 3D force maps. We also do single contact, but I'm just going to show you the force map, which is a discretized set of points, each with a 3D force. So again, the network takes the current image from the camera looking inside the sensor, and then outputs this 3-channel, so XYZ force across a 2D image, which is remapped to the whole surface of the sensor, and we can then draw the 3D force vectors. So let me show the movie. So here's Juanbo pressing on the sensor, and I think the most interesting place is the upper right, where you can see the force vectors being rendered in real time. Lower left is what the camera is seeing, so it can see these deformations. Lower right is what the network is outputting with the 3 channels of XYZ force across the different locations. And it works really well. I'll just go a little bit, jump forward to multi-contact. So there's no limit to how many contacts that can be happening or the size of the contacts. And yeah, so it gets shear and normal force. I think the main innovations here were this soft, rigid hybrid structure, the imaging. We're using both kind of aspects of photometric stereo and structured light. Doing this automatic data collection, it would, I think, be totally infeasible. Here in this project, simulation has played no role. We only use real data. And then this relatively straightforward deep network built on ResNet. And we're able to achieve an overall spatial resolution of about 0.4 millimeters. over a size of 40, 50, 60 millimeters. We can get our force magnitude accuracy. These are all medians of about 0.03 newtons, so it's very, very precise. And we're also looking at the accuracy of the direction we predict up to about 5 degrees median error on a force range up to 2 newtons. We're also having ongoing work by our new co-advised PhD student, Iris Androsov, on miniaturizing the sensor, enabling faster real-time performance, and adding vibration sensing. If you know some of my other work, you know I love accelerometers and vibration and texture and transients. So we want to endow Insight also with ability to feel textures and contacts like that. Overall, I'll just return. These were the motivating observations I saw at the beginning of physical contacts occurring anywhere, softness and robustness being important, looking for solutions that are easy to fabricate, and then maybe using more computational methods, including deep learning, to enable better sensing performance. And so with that, I would like to thank you for your kind attention, and I would be delighted to take any questions that you have.
Thank you very much.
No problem. Let me see if I can just stop sharing. Okay. This was my first presentation in Microsoft Teams.
Thank you very much, Katherine. I see many progress since last 2 years. You gave a great talk to us as well. So is there any question? Yeah, there are many questions. Benjamin, please.
Sure. Hi.
Benjamin, you are
Benjamin, you're muted, I think.
Oh, yes. Hi.
Hi.
Yeah. All right. Thank you for the wonderful talk, Katherine. I'm very intrigued by this, the thumb-like device. I also noticed that it's a sort of more conical. Have you explored various shapes and sort of optimized it for the conical shape versus other types of shapes?
Good question. Actually, Juan Bo is here in the audience, and he could tell you even more about this than I could. But we chose a conical, like a rounded conical shape so that the camera can see the entire inside surface. So we also use a fisheye lens, and it was really important to us that both the back of the hand and the front, so not like a BioTac where, say, the nail is completely numb, but we wanted to see, could we have tactile sensing on all sides? We haven't optimized, we have tested some things, but it's not been extensively optimized. Our newer versions that Iris is leading are more like the size of your thumb tip and like a little bit straighter sides, but still a bit of draft angle. Just trying to make everything miniaturized and make sure that we don't have any blind spots like close to the camera. That's been like the trade-offs, like trying to get everything as small as possible, but see the whole surface.
Thank you. Nice.
So, we have 2 more questions. Shao Yu?
Hello?
If I'm not pronouncing well.
Okay, so thank you for your great presentation, Professor Katherine. Yeah, I have a question about the second tactile sensor, Insight. So you mentioned that the Insight could capture different force when you touch a slide on surface, and in your ongoing project, you also mentioned that it could be captured the tactile or texture characteristic. So I wonder, is it the resolution of the tactile sensor is enough for capture the minimum or fine texture of object surface? Because for some objects, it is difficult to capture those fine texture if you do not use some high fidelity sensors such as accelerometer.
That's a great question. And actually, I should have said, I really admire the work like GelSight and other image-based tactile sensors that are aiming for very fine, detailed spatial reconstruction, so even pressing into a coin or into fabric statically and be able to reconstruct the spatial. And that's not what we're trying to do here. This sensor is more intended to be a robot finger that would manipulate. And so we're not trying to reconstruct those points. We can tell contact and no contact and pretty light forces. I do think it's important to know when contact is happening versus not. But we're definitely not trying to like reconstruct like sub-millimeter level of details. And actually, so far, we don't have a version. We're still working on to get everything to work, to get textures. And here I'm thinking not steady state pressing in. Like if I press my finger into a coin as human, I cannot feel what it says. In GelSight and other beautiful sensors like that can, but I could rub my finger across a surface and tell that there is some relief or tell that there are maybe variations in the friction. And so that's more what we're looking for, is like to complement this spatial distribution of little force vectors of knowing the normal and the shear components of contact with the texture vibrations, more like the Pacinian corpuscles in human or animal skin that are pretty deep in the skin and broad receptive fields and sensing just the overall vibrations that the whole soft skin is doing. Actually, one of my other postdocs did beautiful work as a PhD student with Jan Vassell, who will speak later. He instrumented the human hand with, it's Yi-Tian Shao, and he instrumented the human hand with more than 40 accelerometers and showed that as you tap or do things at your finger, the vibrations travel like way far up your arm, and the vibration, like that whole distribution of where the vibration is traveling, gives you, you can even distinguish textures if your fingertip is numb just from the vibrations that travel through your to your wrist. I'm sorry, I don't know the citation for that, but it was a beautiful, more human perceptual result.
Yeah,
I don't know if I answered your question or brought up other things that were irrelevant. Mohsen, do you want to do one more question, or shall we stop? I can answer questions offline.
There are two more questions. Please keep it short. Inchi, can you please ask your question?
Okay.
Okay, yeah, go.
Yeah. So you said Inji or Huang? I didn't understand.
Inchi, you can start, and then
Okay.
The next will be Huang.
Okay, thank you very much. Thank you very much, Professor, for that wonderful talk. My question is actually really short. It's like, it is because most of studies have shown that both dynamic and static forces are required to detect texture. And do you think that piezoresistivity is the answer for that? Because in the studies I've read, they are more using capacitive, for example, sensors. So.
Yeah, actually, I agree. I don't think that piezoresistivity is probably the best. We try. I'm pretty agnostic as to which sensors. We try a lot of things and look at what works, and it often depends on the task. So I completely agree that dynamic signals are of crucial importance and are often neglected. Today, I chose to highlight work that's more looking at the quasi-static normal force and shear, but I think they need to be complemented with dynamics, and capacitive sensing shows great promise. It's something I haven't personally worked on much yet. But.
Okay, Huang, please ask the last question.
Okay.
We have more, but we don't have time. Sorry for that.
Okay,
People can email me. It's fine. Go ahead.
Thank you for your presentation. I have a question about the first data display. Is I saw you is when you calibrate the sensor, you put it in the flat base, but what happened when we apply to the cylinder shape, or when we scan the tactile display, something like that? I worry something about it.
Yeah, that's a great question.
Sure.
So far, I only showed on a desk, and I am ashamed that it's not yet on a robot arm. I think it should work. We have done some other work I didn't show here around curved surfaces with a slightly different technology, but I have a new visiting PhD student, Christian Schoffman, who's working with Yosan Lee and me to integrate proximity sensing and these RoboTac sensors on an actual robot arm. And so we decided we just needed a visiting PhD student to bring it all together and have a robot move around in the world and feel things on its skin. I expect it will work well as long as we calibrate in that curved format. I think Kyung-So has also adapted his version of the sensor onto being on a robot arm. So I don't think there's anything fundamental, but I didn't show it today, so stay tuned. Thank you again for the questions.
Thank you very much.